So what do we got today? It's either going to be limits, probability, polar coordinates.
Limits.
Limits, okay, cool. Do you have some specific problems?
Yeah, I do. So the first one is sine squared x over x.
As x goes to 0?
Yeah.
Notice, first of all, let's talk about limits, because they're very new to you, I'm sure. In other words, limits is what separates calculus from all math that comes before it. So if I say, what's the limit of x plus 1 as x goes to 2, what is it?
The limit is 3.
Okay, good. If I say, what is the limit of 3 over x minus 2 as x goes to 2?
That you can't divide by 0.
Well, you end up with 3 over 0, which is either, you can call it undefined or infinity.
Yeah.
Neither one will work for now. We'll talk about that later. What is the limit of x minus 2 over 3 as x goes to 2?
That's just 0.
0, right? Is that what you said?
Yeah.
Okay.
Yeah.
So any limit that is either a number over 0, that's undefined, or if it's 0 over any number, that's 0. So limits are easy except for one case. And that's 0 over 0. In other words, in this one down here, if you do a direct substitution, you get 0 over 0. And 0 over 0 is indeterminate. We don't really know what it might be. It might be anything. It might be 0, it might be infinity, it might be a number. It's called indeterminate. Okay? So the only difficult limit problems at all are the ones that end up with 0 over 0.
Yeah.
All right, hold on one second. All right, notice in this one on the bottom, that's what we get is 0 over 0. So what can we do? We can factor the top into x minus 1 times x plus 1. We can or the bottom is x minus 1. Now we can actually cancel that with that, and we end up with x plus 1, and now if we substitute 1 for x, we get 2. That's the limit.
Yeah.
And that's the way to handle 0 over 0, is by factoring. Almost always. All right. So, this problem here. There is a special limit that calculus has not yet figured out how to address, and that's this one.
That's 1.
It is 1, and they teach you this without, in other words, if you were to graph this, the graph looks like this. With that being at 1. So the graph would appear to go to 1 as x approaches 0.
Yeah.
And indeed, that is the limit of that. But if you were to plug it in, it's 0 over 0, and they don't really tell you how they come up with 1. That's because there's something called L'Hopital's rule that you don't learn until maybe the second year of calculus. And that's when you can solve what this limit is. It's very easy to get 1. But they give it to you because so many limits kind of depend on it.
Yeah.
All right, so as long as we know that's 1, well, we can factor the top into sine x times sine x
Okay.
over x. And that's the same as the limit of sine x over x times sine x, right?
Mm-hmm.
As x goes to 0, well, this limit goes to 1, but what does this one go to?
It goes to, doesn't it go to 1?
It goes to 0. The sine of 0 is 0.
Oh, yeah, yeah.
In other words, that's what makes this first one so difficult, is that if you substitute 0 for x, you get 0 over 0. Okay, that particular limit is equal to 1. But the limit of sine x is clearly 0 as x goes to 0. So you end up with 1 times 0, which is 0.
Uh-huh.
All right, what else you got?
The next one is the limit as x goes to 0 of e to the x minus root x over log 4 x plus 2.
Like that?
Yeah.
Well, immediately we can see the bottom does not go to 0.
Yeah.
And that's cool, because the top doesn't either. What's the top go to? Let's just do direct substitution.
Well, it's 1 minus
square root of 0.
0.
So the top is just 1. What's the bottom? The log base 4 of 2. What does that equal to? 4 to what power is equal to 2?
1/2.
Uh-huh. I can replace that with a 1/2. In other words, let's draw it out here. Let's just refresh our logs. Let's say that's equal to x. So now I can say that 4 to the x power is equal to 2. Well, x has to be 1/2. The square root of 4 is 2.
Yeah.
All right, so that's how we get 1/2. So this whole thing is a number. It's 2. That's an easy one. Like I said, the only hard ones are when you end up with 0 over 0.
Mm-hmm.
And you should always try direct substitution as your first step. Most of the ones you're going to have trouble with, when you try direct substitution, you're going to see it's 0 over 0. If it's anything other than that, you won't have any problem. You're only going to have problems when it's 0 over 0, which is called indeterminate. We don't know what that might be.
Yeah. Okay. The next one is natural log of qx over sine squared x, and it's x as x goes to 0.
Did I write it correctly?
Yeah.
Well, what's the numerator go to?
The natural log of 0.
Which is undefined. If I plot the natural log function, here's what it looks like. You can see that the natural log of 0 is close to negative infinity. So if I plug it in, I got negative infinity at the top You can see why it's negative infinity?
Yeah.
Okay. And sine squared of 0 is still 0. Well, when you divide infinity by 0, you're either going to get an answer that's negative infinity or undefined. And
yeah.
this is not, these aren't quite the same thing. Problem is in pre-calc, they don't like to even say the word infinity. So anything that comes close to infinity, they say undefined.
Yeah.
But in reality, they're really different. And you're going to find out that they're different, but let's not even talk about that now. You can tell that when you divide an infinitely large negative number by something extremely tiny, you're going to get infinity. In other words, any number divided by 0 is infinity.
Yeah.
0 divided by any number is 0. So whenever you have these two situations, it's a piece of cake. And this is actually double that. Not only do we have a number divided by 0, we have infinity divided by 0. That's even bigger infinity. I mean, that's not correct mathematical speak, but all right.
Yeah.
What else?
All right. Well, the next one I have is limit as x goes to 0 for sine x over 2x squared minus x.
Well, again, if we do a direct substitution, we have 0 over 0, right?
Yeah.
Okay, so let's factor and see if that gets us anywhere. Well, we can't factor the top, but we can factor the bottom. What do we get?
We get 2x.
No, factor out an x.
Oh, yeah. So it's x times 2x minus x.
Minus 1. Whenever you factor something, in your head, multiply it back together again and see if you get what you started with. If you don't, you've done it wrong.
Yeah.
And that's the way to do it. In other words, you can state whatever answer you want, but if it doesn't pass that last smell test, it's not correct. Okay? So that's always the way to see if you factored something properly, is multiply it back together again. Now, this thing, I know what that is, right?
Yeah.
Okay, so let's separate it into two fractions. Is that a proper separation?
Yeah.
Yes, it is. Okay, so this goes to 1. What does this go to when we substitute x equals 0?
1 over negative 1, so negative 1.
Negative 1, which means the whole thing goes to negative 1. Okay?
Okay.
Okay, what else you got?
All right. The next ones are piecewise function.
Okay.
And I think I can email it, the picture of the
Okay.
graph.
In other words, they're giving you a graph and they want you to come up with the piecewise function as opposed to giving you the piecewise function and wanting you to graph it?
Yeah.
Okay. Go ahead and email it to me and I'll pull it up on the screen here.
Okay.
David Cowan, 1949 at Gmail. You're doing piecewise functions along with limits? What kind of program?
Yeah, limits with piecewise.
I would think that once you hit limits, you're done with precalc. Because limits is the start of calculus. And once you go forward to calculus, I wouldn't think they would go backwards. Piecewise functions it's precalc, totally precalc. Nothing, doesn't have anything to do with calculus.
It should have just sent.
Okay. There it is. All right. Just want to come up with the function for that graph?
No, the limits.
Okay, it does have something to do with calculus. Excuse me.
Yeah.
Excuse me. Okay. So you've had left-sided and right-sided limits.
Mm-hmm.
Okay, so what is the limit of this function as we approach 1 from the left side?
I think it's 2.
No, it's 1. It's whatever it points to. That's the limit right there.
Even if there's a value on the graph for...
Specifically if there is. Okay? Now, what is the limit as we approach 1 from the right?
It's 2. Or 3.
It's 3. Now, those are different. As we approach 1 from the left, it's 1. As we approach 1 from the right, it's 3. Therefore, the limit at 1 does not exist. It only exists if the left-sided limit is the same as the right-sided limit. So, C, the limit of f of x as x approaches 1, is not 2. It's not 1. It's not 3. It does not exist.
Okay.
Huh?
Okay.
Okay?
Yeah.
Let's open up your other document here. So 27?
Yeah.
So as we approach 2 from the left, what is our limit?
3.
Good. As we approach it from the right, what is our limit?
1.
Okay. So what's the limit as x approaches 2?
It doesn't exist.
Right. Because the limit from the left is different from the limit from the right. 28. So we approach 3 from the left.
It's 2.
From the right,
4.
therefore C does not exist also.
Yeah.
Number 29, as we approach from the left,
4.
from the right,
4.
so what's the limit at x equal 3?
4.
Yes.
Okay.
It's not 1. It's whatever the two matching numbers are when you approach from the left or the right.
Yeah.
All right? Those weren't really piecewise. I mean, they were piecewise functions, but as with regards to limits. So definitely, that's calculus, yeah.
Well, those were all of the questions that I had prepared.
Okay.
So I think
there's one other that usually gets you to memorize. What's that limit? Or instead of using theta, let's go ahead and use x. We don't need to use theta. Notice that that is 0 over 0.
Yeah.
What is this limit? Do you know it?
I don't know. I haven't seen this one before.
Okay. This limit is, wow, I might have it backwards. Yeah, I do. I wrote it backwards. If you haven't seen this before, this is the way it should be written. In other words, cosine of 0 is 1. So you have 0 over 0, but
if you do it, if you square the whole thing, right, then it's 1 minus cosine squared x over x. So that's
well, you can't square the whole thing. No. If I take a fraction like 2/3 and square top and bottom, I get 4/9. That's not the same fraction. I can't take a fraction and square both sides, or top and bottom. You can't do that. The only thing you can do to a fraction is multiply it by 1. It's the only thing you can do. It's not like an equation. An equation, you can do anything you want to the left side as long as you do it to the right. But a fraction is different. A fraction you can only multiply by the number 1. Otherwise, you change it. Let's not even talk about this if you haven't gotten it yet. That'll just confuse you. Calculus is a difficult subject because the answer that answers all of these limit problems when you have 0 over 0 is a rule called L'Hopital's rule. Spelled like La Hospital. Okay? And that makes them very easy. Let's take the one that said sine x over x. Well, as x goes to 0, because we get 0 over 0, L'Hopital's rule says, well, you can take the derivative of the top, the derivative of the bottom, substitute 0, and that's your proper answer. The problem is that you have to start calculus with limits, and you don't know what derivative means at this point. But once you learn what derivatives mean, you can solve these very easily by taking the derivative of the top, which happens to be cosine x, the derivative of the bottom, which is 1, and now substitute 0 for x, and you get 1 over 1, and that is what we knew that limit to be.
Yeah.
So if you know L'Hopital's rule and you know derivatives, then these limit problems become trivial.
Okay.
The problem is that they don't know which to teach first. You can't teach derivatives without really teaching limits, and you can't teach limits without knowing L'Hopital's rule for that one. So they solve that dilemma by just telling you that that's equal to 1.
Yeah, so we did derivatives.
Without telling you how they get it. And that's okay for now. But once you learn L'Hopital's rule, you look back on this chapter of limits and you say, wow, why didn't they just tell us how to do that in the first place? It would have been so much easier. And it is. It's so much easier. If I want the derivative of x cubed, I take the 3, I stick it in front, I subtract 1 from it. That's the derivative. Yeah. Taking derivatives really easy for the most part. But like I said, they have a problem as to which to teach first. So do you have any, surely they've given you some limit problems that are tougher.
Well, we just started on them. Like we started on.
Okay. Let me just say this. If the limit is not, if it's not 0 over 0, it's trivial. It's either infinity or 0. Or a number. Right? The only difficulties are 0 over 0. And when you face that, factor. That's the solution. Factoring is always the solution.
Well, since I already did derivatives, I can just...
You could use L'Hopital's rule. If you know how to do derivatives, you can use L'Hopital's rule. In other words, if I give you this original problem where I said you can solve that limit by factoring, and you can, you get 0 over 0 if you do a direct substitution. And when we factored, we saw that this was equal to 2. Well, notice that if we take the derivative of the top, what's that? Using the power rule, 2x to the 1.
Yeah.
Derivative of a constant is 0. So that's the derivative of the top. The derivative of x is just 1. Now substitute x equal 1 and you get 2, the answer. Far easier to get it this way.
Yeah.
Same thing with the limit of sine x over x. This is brutally difficult to figure out until you get L'Hopital's rule. But if you take the derivative of the top, you get cosine x. You take the derivative of the bottom, you get 1. Now substitute. Cosine of 0 is 1.
Yeah.
Let me just, as long as we have a little time here, let me kind of, have you run into the problem of the slope of the tangent line? The essence of differential calculus is figuring out the slope of the tangent line. If this function is y equals x squared, that's what it looks like, that's what it is, and we want to know what is the slope of the tangent line at x equal 2. Notice that the tangent line changes. Everywhere you go on this curve, the tangent line is different. Why is the slope of the tangent line the fundamental definition of differential calculus? Because you still there?
Yeah.
Differential calculus can be summed up in one word: instantaneous rate of change. Up until now, the only thing you've been able to calculate is average rate of change. If you want the average rate of change between 1 and 4, you take the value there, you take the value up there, you take rise over run, the slope of that line is the average rate of change. But how do you get an instantaneous rate of change?
You take the...
The definition of rate of change is rise over run. So if I say, what is the rise over run at point 2? Well, my rise is 0, my run is 0. So I end up with 0 over 0. I don't know what the rate of change is at that exact point. It's the slope of that line.
Yeah.
The essence of differential calculus is figuring out what the slope of that line is. And here's how they get it. They start with a secant line between this point and this point. And then gradually they move this point here down first there. That makes the secant line that slope. And gradually this distance, which they will call h, is allowed to approach 0. So what we're really talking about is not the slope of the tangent line, but the slope of the secant line as h approaches 0.
Yeah.
In other words, as I move this top point closer and closer to the bottom point, that slope becomes closer and closer to the slope of the tangent line. By the time I get down here, I've got a perfect tangent line. And the slope of that tangent line is the instantaneous rate of change of that function. So the slope of the tangent line is huge. Every calculus course, after they get through limits, they start with the slope of the tangent line, because that is the definition of first derivative. In other words, if I use that power rule here and I want to know what dy dx is, and dy dx means the slope of the tangent line, well, it's 2x. Now, as it approaches 2, I just substitute in there, the slope of that line is 4. So I can say that when x is at 2, this function is changing at 4 units per whatever x is. The units on x are. In other words, by figuring out the slope of this tangent line and by doing it as a limit process, the slope of the secant line as the secant line approaches the tangent line, you figure out the instantaneous rate of change of this function when x is 2. And that's what differential calculus is all about, is figuring out the instantaneous rate of changes of functions. So this is coming next. So I'm just giving you a little preview of this. Notice that if I said, what's the slope of the tangent line as x is 4, well, it's a completely different slope. It's that slope. That's a different slope. Well, if I take the first derivative, I get 2x. And now, if I substitute 4 for x, I get a slope of 8. And for sure, it looks like that slope is doubled this slope over here. So the slope always changes. And here's the thing about why is differential calculus so powerful? If I wanted to find out where the minimum of this function occurs, it's clearly down here, right? What's the slope of this tangent line? Zero. At 0, the slope of the tangent line is 0. And we can look at this function and we can see that the minimum would have to occur when the slope of the tangent line is 0. Let's take this function. That has a local maximum right here. And it has a local minimum right there.
Yeah.
Notice what is similar about those 2 points. The slope of the tangent line is 0. So if I said in between that interval and that interval, where's the maximum of the function? Because all you have to do is take the derivative of the function, set it equal to 0, and you discover where that point is. You would get this point, and if you said, well, let's test this interval over here, well, then you'd get this point. So finding where the slope of the tangent line is 0 is extremely important in all kinds of situations. Because where the tangent line is, the slope is 0, is where you have your maximums and your minimums. And that's usually what people are trying to figure out, is where does the maximum of a function occur? You know, if I just give you a random function, some really complicated function, and it looks like this, and I say, well, where does the minimum occur between 0 and 3? The one thing we know for sure is that the slope of the tangent line is going to be 0 at that minimum. It's also going to be 0 there, it's going to be 0 there, and it's going to be 0 there. Each of those points are local, it's called local extrema. They're either local maximums or local minimums. That's differential calculus in a nutshell. And I'm sure you'll get to that before the end of the year. At least I would think so. Unless you reach a point in time like May 1st where they say, okay, no new material, we'll just review old material for your semester final. And that might happen.
We'd be learning stuff.
I don't know. Yeah, I'm not sure. You still got 2 weeks till you get to May 1st. And they may not even start that soon. So I suspect you'll get into differential calculus, and the first thing they'll talk about is the slope of the tangent line. And it can confuse the hell out of people. It's just so different than anything else you've ever studied in math. There's a guy called Raleigh that calculus named a theorem after, Raleigh's theorem. Well, here's the thing. Raleigh was a mathematician in the 1600s. He didn't trust calculus that was just being developed. He didn't think it was correct. He mistrusted it his entire life. He never fully accepted it as being mathematically valid. So the irony is they named one of the most important theorems of calculus after this guy, Raleigh's theorem. But it shows you how different calculus is than any other kind of math that comes before it. It's also considered the greatest accomplishment of humans in the field of mathematics is the development of calculus. It dwarfs everything else. It's the culmination of algebra, geometry, and trigonometry.
Yeah.
Yeah, I'm still here. I think I hear the sound going in and out, but yeah, you're gonna click.
I think my connection.
Is it your connection, you think? Because I'm wondering if it might be my connection, but
I think it's you.
All right. Well, do you have anything else you want to talk about, Lucas?
No, that was all I.
Okay. Well, I've given you enough beginning calculus to let you think about it for a little bit, and hopefully it'll help you a little bit when your teacher gets into that.
Yeah, I think it will.
Okay. I will talk to you next Wednesday. Okay? All right. I don't know. I think I might have lost you again, but talk to you later.